Okay, so we'll begin with what is an algorithm and then look at analyzing an algorithm on the basis of time complexity. So, an algorithm is basically a set of instruction to solve a problem. So, the problem, for example, could be a sorting problem, and you want to sort a list of integers. Then, given an input, which is kind of an unsorted list of integers, the algorithm will do some processing on that input, and you will get a sorted output. Now, we would like the algorithm to be unambiguous in the sense that it should do the same thing for all inputs. So it should not do different things for different input. Okay. So that means if it's a sorting algorithm, it should sort any list of integers. Okay. Now, the same problem could be solved in using one or more algorithms, and among those algorithms, each algorithm could be represented or implemented in different ways. So we are looking at algorithm as a procedure to solve a problem. Now, how you implement the algorithm could be done differently. Okay. Now, most of the time in this course, we'll focus on time complexity or what is called time efficiency. Sometimes we'll also worry about space complexity. So, when I say time complexity, it is like as a function of the input size. Okay, so for any algorithm, we need to identify what is called the basic operation, and we would be evaluating how many times you're running that basic operation, and we'll soon see the details. Now, for space complexity, what we mean is, in addition to the input size, how much space the algorithm takes. Okay, so I say in addition to the input size is because we have to allocate memory to store the input, so we cannot get around with that. But in addition to the input size, does the algorithm require space that grows proportional to the input size? Or does it always require the same amount of space irrespective of the input size? So, for example, if you're sorting, you have an algorithm for sorting, and let us say you're sorting 100 integers. Now, does the algorithm require another 100 units of memory in addition to storing the 100 input integers? Does the algorithm requires another 100 units of memory? If yes, that means if you want to sort 1 million integers, then the algorithm will require another 1 million. In addition to the 1 million for input, you have to allocate another 1 million memory unit. So, if the space complexity or the space requirement of an algorithm grows with input size, that's not a very desirable characteristic. We would like the algorithm to require constant space irrespective of the input size. That means the algorithm space requirement should not grow with input size. So such an algorithm is said to be in place algorithm. So for example, you may require some temporary variables, that is fine. As long as the number of temporary variables you require does not grow with input size, you define the algorithm to require to be an in-place algorithm. That means the algorithm space complexity does not grow with input size. Okay, so now we'll focus on time complexity. So this is good enough to know about space complexity for most of the problems we'll solve in this course. So now we will look at time complexity and look at how we solve the time complexity for a given algorithm. Okay, so the first step in analyzing time complexity is to identify the basic operation of the algorithm. So the basic operation is the operation that is the most time consuming operation or step of an algorithm, and it's typically done repeatedly. Okay, so let us look at an example to understand what is a basic operation. So let us focus on this problem called sequential key search, which is given an array of integers, say from index 0 to n minus 1, you want to search for a specific key in that array. So whether the array has a particular integer. So the logic would be you would loop through the array, and then for every index I, you will check if the element at index I is equal to the search key k. If it is there, that means you are done, and say the key is there. If the key is not there, then we would loop through the entire array and do this comparison for each index, and then we'll come out of the loop and say the key is not there. So if you look at as a basic operation, the operation that is done most repeatedly is this comparison operation, and that's a time consuming operation also within that loop. It's done repeatedly, and for each index you are comparing the search key value with the element at that index. So now how many times you are doing this basic operation? So if you look at this, the number of times you do the basic operation really depends on the search key. If the search key is at index 0, then we just need to do one comparison. If the search key is at index 1, we need to do two comparisons. Now if the search key is at the last index, then we would have to do n comparisons from index 0 to n minus 1. Now the search key may not be there, and in that case we also do n comparisons. So the number of comparisons we do is not a constant, it's varying. So it depends on the search key for this particular algorithm. So we can say there is something called a best case, which is as the name it indicates, it's a minimum number of times we do the basic operation, and it's one comparison. And we can also come up with what is called the worst case, which is the maximum number of times we do the basic operation, and it is n comparisons. So this particular algorithm has a best case different from worst case, okay, and later we'll come back and put these things together. Now let us look at another problem which is the problem of finding the maximum integer in an array. So in this problem, again, you are given an array and you want to find the maximum integer, and a very common sense logic which we or straightforward logic which you should have done in your earlier programming classes is use a temporary variable called maximum, temp max, and assign that in set its initial value to be the value of the element at index 0, and then loop through the array starting from index 1 all the way to n minus 1, and see if at any index we come across an element that is greater than the current value of maximum. So if there is any element at index I that is greater than the current value of maximum, then we assign the value of maximum to be the value of the element at index I, and just continue the process. Now by the time we come out of the loop, we would have gone through the entire array, and whatever the element value maximum, the global maximum is, the value of the system max will be that global maximum, because you've gone through the entire array. Now if you look at the basic operation here, this less than comparison is again the basic operation, which is this less than, they're comparing the value of max with a of I. So the comparison is a basic operation. And now if you see if there is a best case different from worst case, in this particular algorithm it is not like that, because you have to start from index I, go all the way up to index n minus 1. There's no other way go. Even if the element at index 0 is the global maximum, we still have to scan through the entire array. So the best case is same as worst case, and it is like n minus 1 comparisons, because we do one comparison from index 1 to n minus 1, not one at each index. So totally we do n minus 1 comparisons. Now let us look at one more example for time complexity analysis. So this is the problem of deciding whether a given input integer n is a prime integer or not. Now, by definition of what is a prime integer, an integer is prime if it is divisible only by 1 and itself. So, if n is a prime integer, then it should be divisible by only 1 and itself, n. So, anything from 2 to n minus 1 should not divide n. So the logic would be then obviously to try every integer from 2 to n minus 1 and see if n mod I means n divided by I, and see if the remainder is 0. If the remainder is 0, then at least there's one integer in the range 2 to n minus 1 that will divide n and the remainder is 0, means n is not prime. So we can right away stop and say return n is not prime. Then if there is no integer in the range from 2 to n minus 1 that will divide n and the remainder being 0, then we'll loop through this entire loop and then return n as prime. So if you look at now again the time complexity here, the operation that is the most time consuming and is done repeatedly is this division operation of where you really need a to find the remainder. Now, if n is not prime, so for example n is an even integer, then any even integer is divisible by 2. So the first value of index I is 2. You will decide with just one division that n is not prime. On the other hand, if n is really prime, then you have to really go through the entire loop, do one division for each index from 2 to n minus 1. So the number of divisions we'll be doing is really the maximum limit, upper limit, which is n minus 1, minus the lower limit, which is 2, plus 1. So this is the number of divisions we'll be doing, which is n minus 2 divisions from index I equals 2 to n minus 1. Now for larger n, of course, we can say n minus 2 is approximately n. So basically you see that the best case is just one division and worst case is like n minus 2 or approximately n divisions. So in this problem again the best case is different from worst case. Now if you look at this, now again as a algorithm design approach, you'll always try to reduce the time complexity. So if you think about this problem of finding whether a given integer is prime or not, can we do better than n divisions, or means less than n divisions, in the sense that not like n minus 4 divisions instead of n minus 2. Can we do something that is different from n, in terms of the order? It's not n. Can we do it as like instead of n divisions, can we do square root of n divisions or log n divisions and so on, which are all less than n? Later we'll see a table of comparing polynomials. Now the answer is yes in this case, because there is a math property that if you really want to check whether n is prime or not, all you have to do is try from integers 2 to square root of n. If no integer in this range will divide n, then n is indeed prime. So you try from I equals 2 to square root of n and n mod I if it is not 0. So you keep on looping from 2 to square root of n, and for no value of I, n mod I is 0, then after you try all these things you come out of the loop and then say n is prime. So if you look at the time complexity here, again division, but how many divisions we are doing? So the upper limit is square root of n minus 2, the lower limit plus 1. So this is the number of index values from 2 to n square root of n. So it's square root of n minus 1 divisions, and we can say for larger n it is square root of n. Now square root of n is a totally different function compared to n. So this is what I mean. Can we do something that can we accomplish this at a less time? No. So in this case it is possible. Sometimes it is not possible. So whatever we have as an algorithm, that may be the best algorithm. We cannot do something better than that. But in this case, yes, we can do instead of n time square root of n time. So why square root of n is better? Because as you see, as for different values of n, from as n increases from 1, 10, 100 and so on, n again increases the same order, but square root of n is like increasing like this. So if n is say 10 million, then square root of n is just close to 3000, so much smaller. So we would really prefer square root of n algorithm rather than an n algorithm. Okay. So this is how the functions grow. Typically these are the functions we'll encounter. So n and then log n. So log n grows much smaller than n. Okay, so between n and log n, you should be able to say log n is a slow growing function. Now, of course, n grows as same as n. Now, n log n. So log n. Or you can say like this. So n grows larger than log n. So n log n will of course grow larger than n. Okay, so n log n is larger. Now n square again will be larger than n log n, because log n is less than n. So n log n will be less than n square. Of course, n square is less than n cube. Okay. Now all these things are polynomial because n is not in the exponent. So the exponent is a constant like 2, 3 or 1, or even like in this log n is not an exponent. So these are called polynomial functions. Now 2 to the power n is called an exponential function, and then n factorial is a factorial function. Now if you want to say which is a desirable time complexity, you should go for a polynomial function. These two functions are not desirable, so which means you should not design an algorithm which is having an exponential time complexity or a factorial time complexity. Okay, so we'll stop with this for this video.